Alright, let's get started on the first problem of the day, which is going to be LeetCode number 7, reverse integer. Given a 32-bit signed integer x, return x with its digits reversed. If reversing x causes the value to go outside the 32-bit integer range, then return 0. Assume the environment does not allow you to store 30 or 64-bit integers signed or unsigned. Okay. Let's see. One way that we could do this, let's see. So one thing that I'm thinking is that to get the last digit in an integer, we know, or we can mod the number with 10. So for example, 1, 2, 3 mod 10 will be equal to 3. And this is because you can take 120 divided by 10 evenly and have 3 left over. Then we just need to really figure out how to, I guess, multiply the digit back in. What we could do is that we could create an integer list, right? And append the digits one by one. Then at the end, we rebuild the structure. Keeping the sign, of course. And the main idea of that is, well, we store the digits, and as we pop them off from the ones digit, from the ones end, then we add them to the list, and the digit that is in the ones column first becomes the last digit in our reverse. So that works, right? And then we pop until we have a value of 0 within the array, or within the original integer, and then we rebuild the integer. From there, we would be multiplying our current digit by 10 each time, and eventually, if we either hit the limit, then we will return 0, or if we hit, let's say, if we go through the entire list without any problems, then we're good to go. Right, and then finally after that, then we also append the sign to it, and that's sort of, I think, how we can do things. In this case, this would take O of, let's see, log of x time and O of log x space, where x is the original integer. And the reason why this is running in O of log x time is because x is in base 10. So this is log base 10 of x, because that's the number of digits that we'll have within our, stored within our array, our list of integers, as well as the time it takes to break down the integer and then rebuild it. This is, I think, a decent approach. I think that the log x, in terms of the time, is as fast as we can get. However, I'm not entirely sure whether or not it is possible to do this without actually using additional space. I think that's where the interesting thing is. It may be possible to do this without using additional space, though my main concern with that is basically how do you actually multiply in the correct amount, right? So, like, the main thing is just like, how do we know that, okay, when we pop the 3 from here, that we need to multiply this by 300 rather than 3 or rather than 30, right? That's the main sort of problem here that I'm not sure if we can really, I guess, optimize out. What I'm going to do is I'm going to start by actually coding up this solution. And then afterwards, we can take a look maybe at the solution together and see whether or not there's a better solution than log x time and log x space. So first, we'll create the array, and also if x is less than 10 or x is greater than -10, return x. And this is basically, I guess, almost like a base case where if we have just a single digit, so x is between -10 and 10, exclusive of both, then we don't need to do anything because a single digit reversed will stay the same. We can create a digits list, which will be a mutable list of integers. And then we can say var current number will be initialized as x. And while our current number is greater than 0, what we'll do is that we'll do digits list dot add current number mod 10 and current number divided by equals to 10. So this will shift the current number down by 10, by 1 decimal place, essentially in base 10, after we extract the last digit from it and move on from there. We of course also want to preserve the sign. So say val sign is equal to if x is greater than 0, greater than or equal to 0 actually. Well, it can't be 0 because otherwise it would have been returned already. So if x is greater than 0, then it's 1. Otherwise, the sign will be -1, of course. Then what we want to do is that we want to basically, we could probably reuse this current number. And we can essentially check to see if the number will be greater than, or if the number will overflow. This might be a little bit tricky, but let's go ahead and do that. So the problem, I guess, here is that, can we break free from, I think we can do that. So we can do digits list for each number, and we'll return our current number at the end. Current number, of course we should set the current number at the end equal to 1. So this is just starting with the rebuilding. Break down the integer into digits. So from here, what we do is that we will multiply our current number by our number. But first we want to check to see that if current number, let's see, multiplied by our current number, let's see, how do we ensure that it does not overflow, right? Or underflow? Well, in this case, our current number, our result will always be a positive number, right? Because we do the sign part at the end. So then realistically, we have two scenarios. We have a current number multiplied by num is greater than or greater than 2 to the 31. And sign is equal to -1. Or current number times num, well, less than 0, right? Because assuming that it overflows, then it'll be like so. I guess the problem in this case is that we can't necessarily get to 2 to the -31 because it's a positive number, right? So the most we can go is 2 to the 31 minus 1. unless we add a special case for it, which we could actually. So if the sign is -1 and the current number times the number is, let's see, if it's exactly equal to integer dot min value, then we're fine. In that case, then, if it's greater than min value and it's less than 0, then we return 0. The idea is that if we have a negative number which has a value which is greater than min value, so it did not exactly multiply to min value, and our current number is equal to it is a negative value still, right? Because any number multiplied by any other number without overflowing would be greater than the min value, or at least equal to, right? But if it overshoots by more than that and it goes into some negative number that is greater than the minimum value, then we know that something is up. Then we know that we have an overflow that did not exactly equal to the negative min value. At the same time, if the sign is equal to 1 and our current number is, and if we multiply it and it turns out to be less than our integer max, or we can just say current number. So if we result in a lower number after we multiply, we know we overflowed. And we can do something similar here. But if we result in a lower number, but it happens to be negative min value as well as our sign being -1, then we're fine. As long as it is exactly negative, or as long as it is exactly min value, right? So if sign is equal to 1 and our current number multiplied by num is less than our current number, we return 0. If our sign is exactly equal to -1 and our current number is greater than integer min value, and our current number is less than that, then we return 0. We want to do this check first before the other check, because really this check at the end, where the current number multiplied by our new number being greater than integer min value, can actually be for a wide variety of cases. So we want to cut down on the number of times that we actually run through this if statement, right? Or at least all the way through, assuming that we're running on something like the JVM with something like short circuiting, which might cut down at least a little bit in terms of the runtime. Because it will evaluate the first AND statement, then the second AND statement, then the third AND statement, but the first and the second must be true before evaluating the third. So this is overflow for positive numbers. This is overflow, I guess underflow, right? The idea is that if we have a negative number, it cannot underflow beyond, or it cannot go beyond min value. So we can say so we can perform the multiplication here. If the current number, if the new current number is exactly equal to the min value, and Let's see, what happens when we overflow and we hit the last item? Then we just return that number if we hit exactly min value. What if we don't hit exactly min value? Or what if we hit exactly min value, but that's not the last number, right? If we hit min value and it's not exactly the last number, then what would it do? Well, our sign would be -1, and our current number multiplied by our new number, it would be a negative number multiplied by a positive digit, which would be less than our current number, and it would not be greater than, however, it would not be greater than our min value. It would actually be less, well, actually no. If it was exactly at min value and that wasn't the last character, then it would overflow and be greater than, then it would overflow actually. I see. So maybe we want to add another underflow protection here in case we do hit min value exactly. So in that case, let's see. If we hit exactly min value, then we can do indexed. And our index is less than digits list dot size. So if we're not at the end, then we also want to return 0. The idea is that if we've hit integer min value, it should be the last number, otherwise we return 0. If it doesn't happen to be the last digit, then we should return 0 because then the next result will of course overflow it. And of course we need to do a multiply by 10 as well here. Let's see. This is a little bit tricky, as all number problems are. Maybe you recall my previous run-in with number problems. So you actually want to check 10 times this. Okay. Let's see, if the sign is 1, and we do just regular like 123, then 3, of course, 3 or 1 times 30. One times, let's see, 1 times 30, and then that number, oh no, it's, shoot, it's times 10 plus number, and it's like this. My math is a little bit off. We need to move it over by 10 and then add the number into its rightful place. Number times 10 plus num. And if it happens to be exactly integer value and it's not the last digit, then we return 0. Otherwise, in any other case, if we scoot it over by 10 and we add our number and it's less, than our current number, then we know that we've overflowed, especially for positive numbers, right? And then if the sign is a negative number and we scoot it over, and then we multiply it by 10, and then we add some value, if it overflows to negative min value, or if it just overflows to min value, we're fine with that. That basically just means that we've achieved min value, I believe. Let's see. Let's actually take this example. So 2 to the 31 is this value. So if we did 8, 4, 6, 3, 8, 4, 7, 4, 1, 2, I think that's the reverse. Well, that would be a larger number, right? That would be a larger number than what is supported. And that's a larger number than what is possible on the as an input. So I'm not sure actually if it's even possible to get negative, or if it's even possible to get the min and max digits. If it's not possible to get the min and max digits because you can't, the reverse is not possible, then we don't need to worry about that then. And subsequently, we also don't need to worry about, so this is 2 to the 31, negative 2 to the 31, which would be that as an input, which isn't possible, can't be fit in there. And the same thing I think for the overflow. So in that case, yeah, we don't need our last, I don't think we need the last condition that we put in our code. Let's see, if sign is equal to 1 and we multiply it and that turns out to be less than our current number, then we return 0 because we've overflowed. And if we add it and it turns out to be less than our current number at -1, could there potentially still be overflow, or rather underflow? At least underflow that's valid. That's a good question. I'm not sure if there is. Because we can't get, the entire point of this is that if we overflow and we get a value that isn't min value. But of course min value is impossible. So in that case, maybe we only need this. We only really need this very, very broad condition where we say if our current value, if we multiply it by 10 and then we add some number to it, and it turns out to be less than our current number, regardless of sign, then we know that we screwed something up and we just return 0 in that case. Because it's not possible to actually get the min value or the max value as a proper result within our within this equation, I don't think, to build up the remaining number. And so we don't need to worry about overflow or underflow here either. I think that works. Let's go ahead and see if there are any other single digits we've already accounted for. We've already thought about overflow and underflow, which I think are the main corner cases. And we've sort of determined that we can't get the min and max values because as an input they can't exist, because they would start as the same length as the min value and max value, but they'd start with a 7 and an 8, which are incredibly large numbers, right? So I don't think those can exist, and therefore the min and max values are not problems. Could there be any other numbers which cause a similar issue, actually, now that I think about it? No, not really. I think we can't pass the reverse in. We can pass in min and max value, and that would overflow because we are dealing with a sort of sign agnostic implementation where we add the sign at the end, right? And without min and max values, all other values are essentially equal, and we don't need to worry about whether or not it would work for a negative number versus positive number. So I think we've handled most of the cases. Let's go ahead and run our code just to make sure. And we can run through some test cases and things like that. This should be mutable list of int. This is a digits list. This should be return is not allowed here. If we did return at reverse, would that allow us to break out of the loop? Okay. And let's see. Interesting. Oh, we want to start this at 0, which is because we want to start this at 0 times 0 plus the first digit. We don't want to shift it over initially with the 1 and then add our first digit, right? So we can keep the digit at 0. Let's see, where else is this breaking? Mutable list. So we add 3, then we should add 2, then we should add 1, and then we just go in order of that. And this is a var. Interesting. Print line the number. And we should be getting back 3, 2, and 1. Let's see, if it's less than... If x is greater than 0 and less than 10, or if it's greater than negative 10 and less than 0, then we do that. I think we were just hitting the corner case check there. There we go. Okay. Let's go ahead and toss in all the test examples that were given first, and then we can throw in some weird answers as well. Looks like we actually hit an incorrect case on, let's see, it's greater than negative 10 and it's less than 0. That's fine. It's because here we're adding the, when we do mod 10, we're not doing mod 10, at least in the JVM, gives us negative numbers. So I think, interesting. So it's still not quite working. Let's see. This should be giving us positive numbers now once after we do that. But let me double check. Looks like we're hitting a corner case because we're not hitting this print at all. Our current number should end up at 0 times 10 plus our number. Our number doesn't get printed at all, so it seems like it's breaking somewhere else. It's greater than negative 10. Definitely not breaking here. It's not breaking there because it's not returning the original number. It should be going through this while loop, and it should have gone through it because it passed the while loop. Our current number does not start, or does not is not greater than 0, which is why. Okay. So let's deal completely in the world of absolute values. Let's just dealing in absolutes is just so much better. Let's go ahead and run through the test suites again. Also notice an interesting case here where when we reverse the digits, if we have a 0, then our program handles that fine. It multiplies whatever number. In this case, it starts at 0, and it adds 0, so it remains at 0, and that's no problem there. Let's just make sure by adding like 1200, so a couple more zeros, and then also like 1201, just so we sort of see it in action, whether or not we have numbers like that. And then now let's add 2 to the 31 and negative 2 to the 31. It's negative 2 to the 31 is this, and positive would be this minus 1. And we should expect 0 for both of them because the reverse are values that are very, very large. That is not a valid value of negative 2 to the 31. I'm not. This is on my on my calculator. Is this not a valid value? How is this not valid? Integer? Min value, constant field values. Am I missing something? Min value. That it should be valid. How is it not a valid integer as a test case? Like, okay, now it works. Was my calculator wrong? No idea. In any case, let's see. Ooh, I see. Okay, so if we have those values, the problem is that here we take the absolute value of it, and in that case, when it goes to the absolute value, this turns into this, doesn't it? I see. Let me just double check that is the correct, or that is the sort of, I guess, the default behavior. So print line math dot absolute value of integer dot max value, or min value rather. And I expect this to spit out, actually this spits out min value by itself, right? This spits out min value again. Oh, okay, no, that spits out min value again. Right, because we have the max value plus 1, which turns into min value. Okay. In that case, are there any other situations where we don't need, or where we need to account for this? No, I think it's only if we insert in min value, because any other value should be supported and it should go through. So if our current number, if x is equal to integer dot min value, then return 0, because we know we can't process min value normally at all. I'm not a fan of just like slapping in additional cases like this, but given that this is only the case with the min value like this and nothing else, then I think I'm fine with it. Of course, we still need to keep in mind our overflow scenario, because there are other numbers out there that could potentially create an overflow scenario when reversed. So for example, max value, right, is one of those. And really a lot of values actually under max value, so long as when they reverse, they are greater than that. So let's see. I mean, let's toss in a couple of them. So let's change this to 5. Let's change this to 3. Let's change you to a 7. Or let's change you to a 2. Why not? I think those are still valid integers. I was not really paying too much attention to them, but they should still be valid integers that are less than, yeah, that are less or in between the min and max values. Okay, so it seems like it works decently well enough for the edge cases that we wanted to deal with for the initial suite of examples, and we can toss in like something like 0. We expect this to actually no. Well, we can just do or x is exactly equal to 0, right? So if it's single digits in between, or we could do this, right? Because x is neither negative nor positive, but we can include it in one of these. X will be 0 is less than 10, and x is greater than or equal to 0. We could also do it here. Not that it really matters much. And yeah. So let's just double check to make sure that we didn't accidentally break anything with regards to 0. And let's go ahead and run a submit. Let's see if there are any other edge cases that we forgot to account, or if we're good to go. Looks like we did. Interesting. Huh. For some reason, that doesn't look like it broke down correctly. So you got 1, 5, 3, 4, 2, 3, 6, 4, 6, 9. And that didn't seem to actually overflow the way that I expected. Let's go ahead and print the numbers just to make sure. And we'll do a list of debugging here. So it could be the numbers, though I doubt it, right? I think our numbers, our digit scraping logic is correct. I have a feeling that our number times 10 plus num is doing something odd here. So let's do it in pairs. So current times 10 plus num. So our first number will be the digit. The second digit will be our current number multiplied by 10. And then our third number will be the entire expression. I have a feeling that this, for some reason, is producing a value which is actually greater or equal to current number. Let's see. So it starts off relatively benign enough, right? 9, 6, 4, 6, 3, 2, 4, 3, 5, and then the last one is where we start to run into an issue. And interestingly enough, oh, does Kotlin store 32? I don't think that Kotlin stores 32-bit integers by default, does it? Yeah, it shouldn't. Doesn't. And in that case, where is this coming from? Because surely this is larger, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 digits. And 2 to the 31. Looks like it's less. But when we multiplied it by 10 again, it changed. What we could do instead is that we could do and it clearly seems to be that multiplying it by 10 looks like multiplying it by 10 on its own kind of ruined it. So in that case, and given that we can't actually have we can't have the edge numbers in there, is there a situation where could we modify this expression to say that if multiplying by 10 results in a value which does not divide back, is that, because we multiplied it. Yeah, maybe? I don't know. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's that value that is produced is technically still within the limits, within the size limits. But I don't know how that came about. And of course, it doesn't look like the number divided by 10. So in that case, maybe if we just do current number multiplied by 10 divided by 10 is not equal to current number. But I do wonder if this might break something else along the way. Is there a situation where... No, there cannot be a situation where if we multiply by 10 and we add some number and it overflows like that, but it doesn't overflow the other way around where after we add the number, it doesn't overflow. So I think we're safe in that regard and we can continue. So this is another way, I guess, to check for overflow. If we multiply by 10 and divide by 10, does it result in the same number? And theoretically it should. So it looks like this is a valid solution. It does look like it's a little bit slow though I'm not sure if that's based on something else. I'll definitely have to double check the discussion section, but overall I'm relatively happy with this solution. Again, dealing with integer min value and max value can be very, very tricky, and I'm still trying to wrap my head around these solutions. But multiplying by 10, dividing by 10, and seeing if it results in the current number that we have, I think is a pretty decent solution for checking for overflow and underflow. And of course, the main two components of this problem is that we broke them down. We broke the numbers down into digits, and then after that, into their individual digits, into a list, and then we pop them out. And we can try, rather than doing a regular list, we could try using a linked list of integer, right? And this might be faster because then that allows us to insert at the end within constant time, or rather than the amortized constant time. Though it seems like LeetCode is still being very highly variable, so not a huge deal in that case, but something to think about, like amortized versus actual constant time. But I guess in this case it doesn't really matter as much because our digits are very, very limited. We can only really have up to 10 values within our linked list. And in that case, maybe we could even opt for something like an array, right? Because we know that we have a limit on our input. But in any case, those are the sort of main components for our solution. And I hope you learned something, and I'll see you for the next problem.